Okay, thank you. So practically my presentation was started before. Next slide presents the outline of my presentation. The first part of the presentation is motivation. I think the presentation of Professor Marginetti was excellent motivation for our study. So it means I will save some time. The title of my presentation is New Technique for Measurements of Energy Balance During Quasi-Static Tension of Metal. Originally, this presentation was sent by my postdoc student. She didn't come to the conference, so I present his presentation, and so I do it on behalf of my postdoc student. This work is carried out at the Institute of Continuum Media Mechanics, Russian Academy of Sciences. And next slide presents the motivation, the outline of my presentation. I will speak about two things. Practically, I will continue the question of Dr. Berg about influence on environmental condition to estimation of energy balance, dissipated and stored part and the specimen under mechanical test. I will show our attempt to determine the energy balance under quasi-static loading, and after, if I will have time, I will show some of our results about crack propagation. So, if we start several words about motivation, what does it mean plastic deformation? When we speak about plastic deformation, we speak about defect evolution, initiation, motion, annihilation. Now we consider the solid as a hierarchical multi-level system, and each level of the system should be described. There are many ways to do it, and one of the most powerful from our point of view way is to consider the energy balance in the solid. If we go back in 70 years ago, for example in book Frodenthal, it's written that the study of mechanical behavior and properties is possible only in terms of concept which on all levels has the same meaning, and this concept is energy. So 70 years ago we started to speak about energy balance in materials, but from our point of view up to now we have no very good way to estimate and to describe this problem. Here it's just some additional references to the present excellent presentation. The people who was working in this direction. Generally, all work is based on infrared thermography, but for infrared thermography, the main question is how we go from the temperature measurements to the heat dissipation calculation. That's the main reason why we start to use a little bit specific technique under mechanical testing. Next slide presents the geometry of our samples. We was working with a little bit special titanium, but the material is not the main question in this work. I will speak about technique. And technique is the following. We have used infrared camera to measure the temperature of a sample under mechanical testing, and we use additional contact heat flux sensor, which measure the heat flux from the sample. The idea to have two different techniques to measure one thing and compare this technique and results. Here, additionally, here you can see the video extensometer to measure the strain. And next slide presents the detail of experimental setup. We have used infrared camera flip and originally developed heat flux sensor. The idea was quite simple. We have used one Peltier element and connect with Peltier element with some cooling setup. It could be quite simple. One Peltier, big cooling setup, and you can measure the heat flux. You can measure the electrical current in Peltier element and calibrate it according to the heat flux moving from its Peltier. We tried to do it, and the first result wasn't satisfied, and finally we have used two Peltier elements, one for measurements, second it's active system of cooling. And there is a special electrical setup which control the environment temperature, the temperature between Peltier elements, and make a very careful measurement and allow us to carry out very careful measurements of heat flux through the first Peltier. First step, we have calibrated this gauge using using additional setup with control heat flux, and we check the possibility of this element to measure to measure the coupling between heat and elastic properties. So I'm sorry. The simplest way to check the possibility of using of this element is to find the situation that we have when we can find the good analytical solution. If we consider only thermoelastic effect, we have the solution of Kelvin equation, and we can check what we can take from this element. Results is not so bad, and after we go to the classical quasi-static experiments. Here you can see the temperature distribution on the sample in the beginning test and after close to the end of the test. And now the main question, how we can calculate the heat sources in our samples during the experiments. If we write the heat conductivity equation, and generally we introduce the mean temperature in the direction perpendicular to the visible specimen surface, take into account boundary conditions, we can easily write the following equation, which are widely used for thermographic measurements. And the main question, how we can determine this constant tau. A few hours ago it was shown in the same room that this constant tau, it's really a big problem, and this constant describes the interaction with environment. There are several ways to describe this constant. One of the standard for people who working in thermography. We can use the point that the special heat sources, like a point which can be introduced by laser or by, for example, something it can be simply done by soldering tool. And after we consider the heat flux, the heat distribution in the sense without any heat sources. And we find the best constant tau, which give us the zero heat sources in the sample. Its technique allows us to estimate the tau, but we wasn't satisfied, and we try to use our additional system to measure this constant tau. Of course, we can use this Peltier element just simple measurement technique, but for example, one of the possible ways is to use it to find the best value of tau. We can compare the results of infrared calculation based on some value of tau and compare with data of heat flux sensor and find the best value of constant which describe the interaction with environment. We had some problem in the final stage and sometime in the beginning due to inertia of element. But we have very good comparison between data on the middle part of our experiments, and we can easily determine the constant which describe the interaction with our environment. So, based on this idea, we can easily calculate the dissipated and taken into account stress-strain curve stored energy in our samples during quasi-static tests. And now it can be done very easily. We can take stress-strain curve. We can estimate the heat dissipation based on this additional setup or based on infrared thermography. And we have right from our point of view constant which describe environmental condition, and we can calculate the stored and dissipated energy in our experiments. So on the quasi-static test now we can do it practically for any materials, and we have tested, for example, for titanium, for Armka iron, and so on. From my point of view, it's very interesting to see what's possible to take from the crack for the crack propagation. It's very close to a previous presentation, and I want to start. I just present briefly results. I want to start from the Paris equation and show you some attempts which go near the Paris equation. The people try to find another parameters, not stress intensity factor, which describe the velocity of crack propagation. Of course, from physical point of view, the stored energy is the best value to describe the crack propagation rate. We know the value of energy which we needed for crack advance. And it's interesting to measure. Is it possible to measure this value or no? In the previous presentation, it was shown that heat dissipation is a very interesting parameter which can give us a lot of information about fracture. If we consider the energy balance in crack tip, it was firstly it was made by Professor Chudnovsky. We can obtain very unusual, from my point of view, equation for fatigue crack rate. Here you can see plastic vogue, you can see heat dissipation, some parameter which describe the energy which needed to create fracture, and G integral which stay in this part of equation. This equation can describe fatigue crack rate, and we can measure at least this part of this equation. And if we consider that plastic vogue is a part, is linear connected with heat dissipation, we can try to describe this equation only in terms of heat dissipation. That's why we try to do it. And now we have several experiments in collaboration with two research centers. One of them is Bundesuniversity of Munich. And tomorrow will be a presentation of Professor Baer. He will present detailed information about crack propagation and about his study and development of this sensor. I didn't say it before, but the sensor which you have seen in this slide was assembled in this institute during my stay in collaboration with Dr. Baer. Another experiment was made in Tolyatti University, and finally we have three different geometries, three different materials, and we study the heat dissipation from the crack tip in three different situations. The idea every time was the same. We have some data treatment from infrared, we have motion compensation, we have filtration, we have calculation of heat sources distribution at the crack surface, and we have data from the heat flux measurements. From the heat flux sensor, we have continuous curve, and this cross, it is a result of treatment on infrared data. If you are working with high cyclic fatigue, if you test about several hours, it's quite difficult to take with full heat evolution from the infrared measurements. So we have data from the heat flux sources, and we compare it with infrared, and we can investigate the distribution of heat sources based on infrared. Just a few words about results. The results qualitatively the same in different universities with different materials, and we can observe it is experiments with constant stress amplitude. We have two steps of heat dissipation. We have practically constant heat dissipation during crack propagation, and after we have rise of heat dissipation. But originally we expected that on this part crack is stable and don't propagate. But if we take the curve, if we take function which describes the crack length versus number of cycles, we can see that this part corresponds to the slow crack propagation, but in the Paris region. If we put this point, next slide present, if we consider this experimental data, this slide presents the idea. If we take this part of our process and put it on the standard Wöhler curve, it would be located in the beginning part of Wöhler curve. For us, it was quite unusual, but under ordinary Paris regime, we can observe two different regimes of heat dissipation and the crack propagation. Up to now, it's unexplained for us, and we are looking, but for standard Paris law, we have two regions of crack propagation, and we can replace the stress intensity factor only for relatively high crack. For relatively small crack, we propose another approximation, and finally we approximate these two parts using with two quite simple equations. Up to now, it's only experimental fact, and we try to find some theoretical explanation for this. We have found some experimental data which support this idea, but now, up to now, there is no final theoretical description. And summing up all what has been said, I can say that we combine infrared thermography and Peltier-based measurement system for study energy balance under quasi-static tension. The infrared thermography allows us to study the spatial distribution of heat sources. Additional Peltier-based system allows us to measure the real value of heat flow. Accordingly, to obtain data, we can take the value of dissipated and stored energy under quasi-static test, and we have very interesting and unexplained up to now results with fatigue crack propagation. Thank you very much for your attention.
Thanks for the interesting presentation. Any question?
Thank you for the presentation. How did you detect the crack tip position during your experiment? Because we have found that it is a very critical task.
Yes, we didn't. Yes, it's true. Yes, it's the same problem. That's why we try to take all heat which dissipated from the specimen surface. We had Peltier which cover all process zone, and they take, from our point of view, all heat which dissipated in this area. From another part, from thermography, we just calculate the heat sources field, and we don't find the crack tip. We solve this equation, take into account exchange with environment, and find the field of dissipation. After we integrate, not in some area, we just integrate all what we have. So it's, yes, I know the problem how to find the crack propagation, but in this situation, I think we are a little bit avoided of it. Okay.
Other question? Okay, so we completed the session. I hope to see you tomorrow afternoon to the next session of thermal meters. Thanks to everyone.